All right, we're going to go over the back side of the review. Now it says describe the end behavior of the polynomial function, then graph the function. Let's look at this. Well, what will the end behavior be? Do we know off the top of our head? Well, the leading coefficient, that's a 1. So what's positive? This is a cubic function because 3 is the highest exponent, and that is odd. So that actually already tells us a lot about the end behavior. In general, cubic functions tend to look like this when they are positive. Okay, so they're going down and to the left, up and to the right. So we should have a rough idea of what it's going to look like. Now, there are going to be some few variations, and that's really what we're going to have to investigate as we graph it. So let's try and get a few more points at least, so we have enough information to graph. I'm going to make an XY table. Okay. Now it seems like it goes up 1, 2, 3, 4, 5, 6, 7, and probably down 7 as well. So if the y value is greater than or less than 7, I'm not going to really worry about it. I'm going to plug in some x values. I don't necessarily know what's going to be good. I'm just going to go from -2 to +2. If that doesn't work, I'm going to have to keep on plugging in more x values. Well, let's try -2. -2 will give us, well, -2 cubed, which is -8. -3 times -2 squared, which is 4, plus 4. Do a little bit of math. Let's see what that gets us. Okay, so that was a little quick. I'm trying to get through this so you guys have enough time for the test, but we have -16. Okay. So let's think about it. Is that something that we're going to want to graph? Probably not. Hopefully, one of these x values will give us an indication of where the important parts of the graph are, at the very least. So let's try -1. So again, we're seeing what y value will we get from -1? -1 cubed is -1. Squaring -1 gives us a +1. Do a little bit of math. We have the following. Okay, so that gets us 0. All right, that's something that we can definitely graph. So I'm going to go ahead. I'm going to plot in, let's see, red. I think that'll be more visible. Again, if we go left 1, we're going up or down 0. Boom. Okay, so we're on the map. That's good. That should make us hopeful. I think that if we just keep going right, we should be able to get some good y values that we can graph. Let's try 0. Hopefully you already had an idea of what the y-intercept would be from the beginning. This is pretty straightforward. This is going to become 0. This is going to become 0. That's going to become well, that stays a 4, and the whole thing ends up being 4. So right now when we go left or right 0, we're going to go up 4. Boom. 1, 2, 3, 4. All right, so that's another point. Sweet. We're going to go ahead and keep going right, because that seems to keep giving us good values. Let's try 1. Cool. 1 cubed. Wrong color. 1 cubed is 1. -3 times 1 squared is 1. Plus 4. This is 1 subtracted by 3. Plus 4. 1 subtracted by 3. -2 plus 4 gives us 2. All right, so 1 will give us 2. If we go right 1, we'll go up 2. Boom. Right 1, up 2. And let's try, we actually might have to do more than just these x values, because we're only seeing just a little bit of what should end up being a cubic function, or what is a cubic function. So let's try 2. 2 cubed is 8. -3 times 2 squared is 4. Do a little bit of math. Okay, so it looks like we're going to have, oh, interesting, 8 and 4 make 12. 12 minus 12 is 0. So 2 gives us 0. Go right 2, we're going to go up 0. Okay. Again, if we have a vague idea of what a cubic function is, we're definitely going to need more points in this. Because right now it seems like they're both, maybe, just maybe, it might seem like as we go left we go down, as we go right we go down. So let's keep on going. 3. So if we plug in 3, go ahead. Let's delete that. Okay, so if we plug in 3, we'll get 3 cubed. Okay, so we'll get 3 cubed. 3 cubed is 27. Negative 3 times 3 squared is... Oh, well, hey. We actually have 27 subtracted by 27 plus 4. Perfect. That's a fairly easy number. Oh, now we're back up at 4. Okay, so now it should already start looking a little bit more familiar as a cubic function. Right now we can already start, if we're tracing our tracks, it should end up giving us something like this. Now, we already know that if we go as far left as 2, we're going to be down negative 16. So right now we can actually kind of finish this portion of the graph off, knowing we're never actually going to reach this negative 2 as long as we're on what we have here. But the question is, well, if we go right 4, 1, 2, 3, 4, are we going to see it, or is it going to be somewhere way up high? So let's verify that it definitely seems like it's going to be off the charts, but let's just double check. Right now we're going to have 4 as our input, so we're going to go right 4. How far up do we go? Well, 4 cubed is 64, because it's 4 times 16, right? 64. Subtracted by 3 times 16 plus 4. Now, if you do a little bit of math, you should be able to find out what it is. I'm actually going to do something that you're going to not like. I'm going to say, well, 64 is 4 16s. Yeah, you might hate that, but 4 16s should be 64. That is kind of how we got here. Well, 4 times 4 times 4, really it's 4 times 4 times 4. The reason I like to think about it that way is because I'm already looking at 16s here. I have 3 16s that I'm taking away from 4 16s. Well, if you have 4 of something and you take 3 away, you're only left with 1. So we're actually just left with 1 16 plus 4. That gives us 20. Ba-boom. 20. That's way off the charts. We're not going to be able to see that. So negative 4, we're not going to exactly see where that ends up with what we got. Now again, the end behavior, it's kind of what we expected as we go left, and this is how you write it. As x approaches negative infinity, as x becomes more and more negative, the f of x value becomes more and more negative, meaning it's going down. So as we go left, we're going down. Now look, as we're going right, it seems like we're going up. So you write that as x becomes more positive. As x approaches positive infinity, f of x becomes more positive. So it keeps going up to positive infinity. And that is, that's that. Now we're going to look at something in vertex form. This is just a cubic function. I'm going to rewrite this. So it's a little bit of color coding. Negative 1 is our multiplier, which means it's going to be flipped. I'm actually going to write it as if it weren't flipped, and then I'm going to rewrite it the way it actually is, which is flipped. Subtracted by h. Again, this is just intercept form, so our h value is actually 1. Then we're adding k. Adding k, well, our k value is 3. Now, this is going to kind of tell us the shape. Is this, well, it's a exponent of 3. This is also going to tell us a lot about its shape and that it's flipped. The vertex, though, remains exactly as we see it. The x value is 1. The y value is 3. We're just strictly looking at our h and our k values. This is going to be a lot of points on the test, just that you can find this, because that's the power of vertex form that you can apply to several different functions and several different behaviors. So we go right 1 up 3. Okay. Now, well, there's no stretch, so it's going to be the basic characteristics of a cubic function. So normally, again, don't write this down if you're copying it down, but normally you go right 1 up 1 cubed. Well, 1 cubed is 1. Then you go right 2 up 2 cubed, which is 8. Somewhere up here, I'll just put a dot, somewhere up there. Now, normally you go left 1, so if it's negative 1 in the x direction, in the y direction you're going negative 1 cubed. Well, negative 1 cubed is negative 1, so in the y direction you're going to go down. Okay, negative 2 in the x direction gives you negative 2 cubed, which is negative 8 in the y direction. This is kind of the general look of the cubic function. Now the thing is, it's flipped. It's flipped. This multiplier says it's flipped. So actually, instead of going out 1, up 1, we're going to go out 1, down 1. Instead of going left 1, down 1, we're going left 1, up 1. And instead of going right 2, up 8, we're actually going to go right 2, down 8. 1, 2, 3, oh, I should be right about here. So basically, it's the flipped form. So I'm going to go ahead and erase this and create a flipped form. Boom. And boom. All right, there we go. And I'm going to keep this nice looking vertex. And it should look roughly like that, and that's fine. That's fine for now. Now we're going to say the domain. Well, it looks like it goes infinitely left, infinitely right. Nothing's stopping it. So we do this fancy R. All real numbers, range. It seems to go infinitely down and infinitely up. So boom, fancy R. All right. Now the next one. So we have another function. This is a square root function. What color do I need? Oh, let's go with pink. Or yeah, pink. So this is the shape that we're looking at. Notice there's no multiplier in front of it. We assume, or it's implied, that this is a second root and nothing other than that. I'm going to rewrite it form. We have f of x is equal to, and I'm just rewriting this instead of the square root. I'm going to just write with an exponent 1/2. Again, that is the same thing. This 2 in the denominator is the root. And wow, now that doesn't look too different from what we were working with before. So we just have to make sure that we remember that the shape is going to be that of, well, something with an exponent of 1/2, which is going to be the inverse of a parabola with a few restrictions. So we have 1/2, we have x. Maybe I need to move this off to the right just a tad. Okay, so right now I'm going to rewrite this in terms of h. Well, it's x minus h. Well, what do we have to subtract to get to what's essentially plus 3? Well, if you subtract a negative 3, that is x plus 3. So that's our h value, is negative 3. If that's too difficult, just think, what x value will give you a 0? What x value will give you a 0 right here? Well, negative 3 would give you a 0. Now we're just going to go ahead and add our k value, which is simply 2. Nothing tricky about that. And what that gives us is the vertex. Vertex is our h value and our k value as x and y respectively. So we can go ahead and plot that vertex. That would probably be our first point. Go left 3, up 2. Boom. Now, remember, it's going to be a quadratic on its side, but there's going to be a restriction. So again, it's going to be a quadratic on its side. So up 1, out 1 squared, up 2, out 2 squared, which is 4. 1, 2, 3, 4. Then up 3, out 3 squared, which is 3 squared is 9. So 1, 2, 3, 4, 5, 6, 7, 8, and 9. Hopefully I counted that right. Now it's going to also, well, if we were to not worry about restrictions, it'll end up being that same thing on this end as well. So you end up having that parabolic shape or parabola shape like this. Boom. And then you end up having that same thing right here. Let me try and not mess this up. Now the trick is, again, if we remember the vertical line test, this is violating that, meaning that we have to have some sort of restriction. We have to take half of the shape away. Well, if you're looking here, notice we don't have anything in front of this square root. We don't have a negative, so we're actually looking at the positive root of this. We're looking at the principal root. So we're only taking the top half is what that means. If this was a negative, you'd be taking the bottom half. So that is what your shape looks like. It's just half of the parabola. The domain is how far left and right it goes. The domain, well, how far left does it go? Seems like it goes as far as negative 3, including negative 3. Well, it includes it. We'll put a bracket, negative 3. How far right does it go? Well, this keeps on going to positive infinity. All right, now what about the range? Well, how low does this... Alright, I'm not going to say it in the way that rhymes, but how low does this function go? How low does this go? Alright, so, well, it goes as low as positive 2. And then it goes up to positive infinity. Simple as that. Alright, now we have our, we have a absolute value problem. Okay, so this is absolute value. We'll treat that like parentheses. So right now it's just going to be the absolute value of x. Well, where's our h? Well, our h is going to be 0. X minus 0 is x. So if we're to write it in vertex form, you might want to include that just to make sense of it for just a little bit. Now this negative 5, well, that's the same thing as adding a negative 5. So adding a negative 5. Now we have our x and our y values for our vertex. Sorry for fumbling. I think I'm getting a little tired. But we have 0, negative 5 for our vertex. And that is cool. We go down 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. All right. Now, this is going to be like a line. It has no multiplier. So that means it's going to have a slope of positive 1 whenever there's a positive value. And essentially, this absolute value operation is not doing anything to positive x values. So all the positive x values, it's just going to go up like as if it were just a slope of 1x. Now, if you plug in negative x values, meaning we're going to the left, negative x values will almost activate this absolute value to basically flip the sign, just like a negative 1x would do. So this ends up being a slope just like negative 1x. It's a slope of negative 1. All right. And that's it. It's just like a parabola, but straight arms, and well, it's not really like a parabola at all, but maybe if you want to look at it that way, that's cool. So, domain, it seems to infinitely go left and infinitely go right. We'll go ahead and call that all real numbers. Range, it goes as low as negative 5, including negative 5, and then it keeps on going up. So we'll say all the way to positive infinity. All right, let's take a peek at this. We have a cubed root. So again, I'm going to say, let's look at this as if it were a exponent of 1/3. So y is equal to the exponent of 1/3. I'm going to go ahead, jump ahead, and say this is x minus h. H would be 2 in this case. And then if we were to add k, if we were to say plus k, this would actually be 0. So right now we already have the vertex. We already know that the vertex is going to be this guy right here. So right 2 up 0 is our vertex. Okay, well, cubed roots are, again, if you were to visualize, I think the inverse would kind of look like this. The inverse would look like this. Well, what if we found the reflection across this? What if because again, this is the inverse of a cubic function. Well, it would end up doing something like this, if you believe it. It would end up doing something like this. Like that. And this way. And then go across 8, so left 8. Cool. I just found the reflection of it. That's one way of going about it. Otherwise, you can just start plugging in x and y values. Let me get rid of all that junk. Okay. So the domain and the range, well, it seems to go infinitely left and infinitely right. So we'll say all real numbers. And even though I did a bad job of drawing this, well, this is gradually still going up infinitely and also gradually going down infinitely, so the range is also real numbers. Okay, so now I'm going to look at this this problem, and it has an extraneous solution. The reason is, well, this, a square root, it's the inverse of a quadratic, right? We kind of already went over that. Well, one thing that we had to do when we when we found the inverse of a quadratic, or the inverse of a parabola, well, when we put it on its side, we had to take half of it away. We had to restrict it. Now, the interesting thing about this is if we kind of blindly go about solving for x, we're going to turn it back into a quadratic, and we're going to find two solutions. But because this is actually it's just the principal, the positive root of all this, and it's not the positive or negative, well, only one of these answers that we get is going to satisfy the positive root, while the other one would satisfy the negative root. Alright, so enough of that. Let's look at this. We have the square root, the principal root of 2x subtracted by 3, and we have x subtracted by 3. Now, if you do something like this to a square root, let's see, we'll go ahead and we will square that. Hopefully you see that it'll cancel out, but we have to do that to the other side. Now we're going to have 2x subtracted by 3 is equal to, well, this is going to give us this. Do not overgeneralize. Make sure you take every extra step to see that it is going to be something that requires some fairly complicated distribution. It's not simply x squared and a 9. So right now it's x times x is x squared, x times negative 3, and negative 3 times x gives us negative 6x. And then we have negative 3 times negative 3, which is a positive 9. Then we have 2x subtracted by 3. I'll do a little bit of math. I'm going to go ahead and add 3 to both sides. Now we have 2x is equal to x squared subtracted by 6x plus 12. Again, I just added 3. And then we're going to subtract 2x, so we get 0. X squared subtracted by 8x, I believe, plus 12. Alright, now we can go ahead and factor. Boom, x. Let's see. 2 and 6 seem to be good, but they both have to be negative because we're looking for a positive product, negative sum. Boom. So that is going to give us the following. It's going to give us two potential answers. It's going to give us x is 2, and then x is 6. We have, let's try 2 first. So I think that's extraneous solution. Let's check it out. So we have the principal root of this. Well, it's going to be 4 minus 3 is equal to, the x value will also be 2. Again, I'm trying this guy out right here. 2 subtracted by 3 is negative 1. Well, is the principal root, the positive root of 1, which is 4 minus 3, equal to negative 1? No, because the principal root of 1 is 1. And 1 is not equal to negative 1. So therefore, that is our extraneous solution. Okay, that's cool. Well, let's double check, because we want to be thorough. This is the test. So let's take the extra time to say, what is this going to look like? What is 6 as x going to look like? Well, we have 2 times 6, which is 12, subtracted by 3. It's the principal root, the positive root of that. 6 subtracted by 3 is 3. Okay, well, 12 subtracted by 3 is 9. Is the positive root of 9 3? Well, yeah, the positive root of 9 is 3. 3 is 3. So that's our guy right there. That is our only solution.